Howdy everyone, welcome back to my channel. This is Professor Parks, and today we will be talking about one of my favorite parts of, or portions of astronomy history, and that is the Copernican Revolution. It is an excellent example of how science ultimately corrects itself, where you have a sort of crisis of a model or an idea of what you think the universe is like, or what we think the universe is like. And then observation upon observation starts to tell you that maybe you need to rethink what you're doing. And then it gets rethunk and you come up with a much better idea of how to describe the universe. So yes, this is of course part of my ongoing series on the solar system. Today is kind of going to be a twofer, because I've been a little bit chaotic in getting these videos out. So just to basically to make up some time, I'm going to be talking about, as I said, the Copernican Revolution in this lecture. And then in the next one, I'm going to be taking on the subject of gravity and how that can be used to gravity and how that can be used to describe orbits. Really the physical cause for why planets orbits around stars, why moons orbit around planets, why galaxies orbit around each other, things of that nature. But first, I want to say hi to Judy and Cygnus, who are in the chat. Judy had mentioned that I had done a observatory tour here at George Mason, and that is, if memory serves, I attempted to do that, although I did think I had some internet problems when I actually went into the dome. That reminds me that she asked if there had been any changes with our sends, and yeah, I think there have been a few couple three changes. I don't remember exactly when I took that video, but as I mentioned to her, one of the things that's on my great list of things to do is to make a more polished video. Probably not do it live because of internet issues, but basically go up there, record, and then stitch together a video which really highlights the capabilities that we have here at George Mason, from a teaching standpoint, from a research standpoint, and also from an outreach standpoint. So, all right, let us get down to it. So last time I was fumbling my way through the seasons and so forth. At some point, I talked about the conception, or basically the first studies of the heavens and the first logical ideas about what our universe is, or where we are in our universe. And these came from the Greeks. To be honest with you, I don't know of where it started in the East. I really do need to look into Eastern astronomy, because I honestly have very little understanding of who the Hipparchus of China was, or Japan was, or what happened. So I'm going to stay Western biased and talk about the Greeks. The Greeks were the first people to really write down, hey, this is what the sky looks like, and this is why we think it looks like this. So, as I mentioned before, Hipparchus did a complete study of the night sky as he could see it, both in position and brightness. And Aristotle then came around and said, oh, all right, well, the reason why it looks that way is because we have Earth at the center. Earth, the sphere, is at the center. It's composed of four particular elements: earth, wind, fire, and air. Not earth, wind, fire, water. Hey! And then the celestial bodies, which act differently, were actually composed of something called ether. Now, this was a good general description of what this was. And Aristotle then also came up with the idea of basically ether structures, of circular structures surrounding the Earth. So the Earth was center, and then right above that was a sphere, a celestial sphere, if you were, or an ether sphere that contained the moon, then the sun, and then the planets. Each had their own sphere, and then the background stars comprised of the largest sphere. And each of those spheres moved in with a particular speed of their own, and that speed was uniform, because apparently uniform circular motion is really groovy. And so Aristotle thought, that has to be how things work. is uniform circular motion. And he believed these spheres, basically, like I said, rotated with respect to each other at their own particular speeds or velocities. And he left it at that. The problem is that almost immediately, Hipparchus has already shown you got a problem. And that problem is with the planets. Now, as folks that I've interacted on the internet love to point out, planet, the term planet means wandering star. And that is correct. The Greeks' term planet from the Greek means wandering stars. Because to them, they saw these bright lights in the sky, Mars being red, Jupiter and Saturn being more brownish, yellowy. They saw these bodies as star-like, but also they saw them move more rapidly with respect to the background field of stars than any other object in the sky save the sun and the moon. And so they refer to them as wandering stars for planets. And because this was pre-telescopic, is telescopic a word? Yeah. Pre the advent of the telescope or the invention of the telescope, they could only see 5 of these wandering stars. Mercury, Venus, which really can only be viewed at the early morning or early evening. Mercury is never seen later, like in the middle of the night, because it's always close to the sun. Venus, again, is seen only in the mornings and evenings, although you can see it a little bit later or earlier, I guess, than Mercury, because it's obviously further away from the sun. And then you have Mars, Jupiter, and Saturn that can be seen at any time of night, depending on where they are. And so this basic idea, basically these wandering planets, passing through the sky faster than the stars. All right, so Aristotle's idea seems to check out, the first approximation, in the sense that, you had all these nested spheres, and each one of them has their own speed. Then, yeah, all right, you can somehow approximate that. But the problem is that these wandering planets do something else. And this is known as retrograde motion. And all of the planets really do this, but I'm going to be concentrating primarily on Mars. And you'll understand that as we get further on. This is an image of Mars taken, I believe, or images of Mars taken between, I think it's October of 2021 and then March of 2020, October of 2011 and then March of 2012. But really the gist of it is, when you look at a planet from night to night to night, and it's doing the normal thing or the prograde motion, then it's going to appear to move from west to east across the background field of stars, in this case, say the constellation of Leo. But at certain points, it's going to seem to slow. So if you looked at the interval, if you were looking at this at a very regular interval, the distance it travels across the sky appears to shorten. It gets shorter and shorter until it kind of seems like it stops. And then it goes backwards. It actually goes from east to west for a few weeks. Again, it then seems to slow up, stop, and then go back the other way. This is what we call retrograde motion. The apparent motion of a planet to go forward, slow up, stop, reverse its direction in space, slow up, stop, and then go back again. The other thing to note, which is of importance, that I hope you can see in this slide, is that the planet brightens as it does this. The planet noticeably gets brighter in the sky as it undergoes this loop-to-loop or retrograde motion. So whatever model of the solar system you want to build, it needs to take into account both of those phenomena. It has to explain why the planet seems to go backwards, and it also has to explain why it seems to get brighter as it does so. Because again, any model or any hypothesis has to account for all observed phenomena if it's going to be considered valid. Well, I'm going to skip that little thing. And so here again, here is Aristotle's model of the universe. Very, very simple. Nested spheres made out of ether. Geocentrism, as I mentioned before, basically the Aristotle again that you had. I mentioned before Aristarchus of Samos. Aristarchus used logical reasoning or deductive reasoning to say, all right, if the sun is so very bright, then obviously it's the luminous, most energetic thing that we know of, so it must be the center. Whereas Aristotle and others, and most others, took the opposite approach of, well, we live here, so obviously that's we must be the center of all things. And that idea, that sort of anthrocentric idea, has stuck around, and actually was one of the reasons why the Aristotelian philosophy continued on into the Common Era, is because of that. Now, like I said before, one of the arguments that Aristotle had against the fact that the Earth, or had against the Earth's motion, so why the Earth was stationary, one of the reasons was because of if the Earth was going around the sun, you would expect to see something known as parallax, or in a very dramatized way, or not to scale way at all. Let's look at this situation where you have the Earth on one side of the sun, and you're looking at a nearby star that happens to coincide to be in the constellation, or rather, the asterism of the Big Dipper. And then 6 months later, you notice that it actually shifts to the other side. And because of your perspective, because of basically your line of sight changes as the Earth goes around the sun. Now, this is grossly out of scale, and this is really the crux of why it was rejected, because the Greeks may have had the conception that that is really what you would see. You would see a star move that much as the Earth going around the sun. In actual fact, stellar parallax is tiny. It is a very, very small effect that you actually need fairly simple, fairly sophisticated, not so much fairly sophisticated instruments in this day and age, but a very, very sophisticated observational strategy in order to actually be able to see this effect and to measure it accurately. At this point, a lot of it is done, or almost all of it at this point is done through satellites. Specifically, the European satellite Gaia, go Europe, that has done marvels when it comes to parallax. But anyway, as I said before, the Greeks were left with two options. They could either reject the idea, or they could either say, all right, we don't see parallax. So either that means A, parallax doesn't exist, that we are in fact stationary, or B, that the stars are so far away, this parallactic effect is not noticeable by eye. Because as a star gets further and further away, the shift that it does across the sky would in fact get smaller and smaller and smaller. They chose the former. They chose the idea that the stars could not possibly be that far away, because they couldn't possibly be that bright. And so they said, Earth is at the center. I will go over parallax later when I talk about the cosmic distance ladder. How did we get around, or how did the Greeks get around this? How did the Greeks solve this particular dilemma of retrograde motion? Well, Aristotle, as brilliant as he was a natural philosopher, really, in the sense that he literally just did philosophy. I don't know how much mathematics the man did in practice, but he certainly didn't create any kind of mathematical backing to his model. So we're left with Ptolemy. Ptolemy was a Greek who lived in Egypt, and I've forgotten exactly when he lived in Egypt. In or about, I think, 100, 200 BCE, somewhere in there. I don't know. Anyway, Ptolemy set about taking Aristotle's ideas and philosophies and Hipparchus's observations and reconciling the two. basically saying, okay, well, Aristotle's model cannot explain retrograde motion. So what I want to do is I want to be able to create a model that not only conceptually explains retrograde motion, but most importantly, it can predict where the star, or where the sun, the moon, the planets are going to be at any later date that I choose. So if I want to know where Mars is going to be in the sky precisely 2 years, 3 months, and 2 days from now, my model can tell you that. And that is a cornerstone of science, is that it can you can use it as a predictive tool to figure out what the universe is going to look like, or how the universe is going to behave somewhere further along down the line. And he created this, which I'm going to switch screens, make it a little bit, make it bigger. Can I make this bigger? Probably not. All right, I'm going to, where is it? Can I do this and not screw things up? Probably not. I can. Woo! Yeah, all right, so I had to move it onto another screen so that it's more manageable. Hey, I could even make it bigger. Woo! All right, Rob to Tech today. So, right off the bat, ironically enough, and I'm surprised this wasn't a huge red flag to anyone, well, or at least to Ptolemy, was that one of the things that Aristotle said, and it's kind of a real big important thing, is that the Earth is in fact the center of the universe. Well, Ptolemy said, I can't get that to work. I can get it close. But what Ptolemy did was he actually put the Earth slightly offset from the center of the universe. And so, but he pretty much kept everything else. The other two big ones that Aristotle really liked were that all celestial bodies moved in perfect circles, and the second one was they moved in uniform circular motion. These two Ptolemy was able to actually incorporate into this model in a very, very kludgy, very, very computationally intensive way. Now remember, this is back when they were using abacuses, no calculators, no computers. This was all done by hand. So what he did was he decided that, let me see if I can find, so what he did was he basically said, all right, so instead of the Mars existing on its own sphere, in this case shown as a circle, own sphere orbiting around the Earth, what it's going to do, and which is known as the deferent, what he's going to do is that Mars actually orbits around something known as an epicycle. I don't believe that Ptolemy thought these were physical objects, physical spheres, but I could be wrong. I haven't read through the Almagest in all of its glory. The Almagest is the book that he wrote to describe all this. And so he said the Mars goes around in what he called an epicycle, which is a circle which has its center on the deferent. So here, in that deferent, and so the circle is centered here. This is the this is the point at which the epicycle is centered on the deferent. This is essentially the line of sight of the Earth to the sun, to Mars, out to the sky. Let's get rid of that. And so let's set this thing in motion. And down at the bottom, you can kind of see that retrograde motion. P is the line that corresponds to where we think the planet is in respect to the zodiacal signs. You can see that it stops, goes back, comes back around. Ptolemy's explanation for why we see retrograde motion is that, and why it brightens when it does so, is that Mars literally goes backwards in space and gets closer to us because of it running around on these epicycles. And you can tweak this essentially, and you can use this model to, as I said, predict where Mars is going to be at any particular future time. And you can do this with other planets as well. You can do Jupiter. Obviously, it's going to move slower because it's further away. And you can do Saturn, which is even slower. And yes, Cygnus, I as much as I might seem like I'm getting down on Ptolemy, this is a huge mathematical feat. The fact that he was able to even come up with this and make this work for as long as it did is incredibly impressive. Again, considering that he did all of this by hand and subsequent people made changes to his model again by hand. And you can see over here that for each particular planet, there's at least four. Four. What's the word I'm looking for? Variables or characteristics. Variables. That's the word. Variables that you can change in order to make things work out. So you can change the size of the epicycle. That's going to have a consequence on how long the planet will go through retrograde or how large the retrograde is. You can change he actually set it to 0. You can change the eccentricity. You can change how fast things are moving, and essentially where the planet is furthest away from the Earth and so forth. So there are variables that you can tweak, that Ptolemy can tweak in his model to basically make his math work out. And that's what he did. And that's what subsequent people did. Now, problem comes in. Now, in actuality, how do we explain retrograde motion now? We explain retrograde motion as simply a perspective effect or a line of sight effect, where here you have the heliocentric model, where the Earth is revolving around the sun. You have Mars revolving around the sun in a further orbit. We know from Kepler, which I'll get into later, that, and really Newton, as I'll get into later, that Mars orbits slower, it travels in its orbit slower than the Earth does in its orbit. And so the Earth is going to lap Mars. So if we take 5 points in time, what we can see is if we're on 1, we look at Mars and we look at this background field of stars, we see it here. Look at 2, we have moved significantly in our orbit, Mars not so much. Mars appears to be moving pretty much in a prograde way. But once we get to 3, you can see that because of our shifting position relative to Mars, the appearance of the location of Mars in the night sky appears to go backwards, and then back on, then so forth and so on. The reason why, again, it's brighter is because that is one thing that Ptolemy's model did get right. We are, in fact, closer to the planet when it goes through retrograde motion. In fact, we are at a position that is called opposition. We are close, and that is when the planets in question, Earth or Mars or really any 2 planets, when you're in opposition, they are as close to each other as they're going to get over the course of that particular year or so. Obviously, that particular distance also changes because the orbits are elliptical, but we won't get into that right now. And I think that's it for this slide deck. So I will just do that. So that should be it, right? I mean, Ptolemy came up with a model. Bing, bang, boom. You can explain stuff. Why don't we use it now? Aside from the obvious answer of, it's wrong. The reason why we don't use it is that Well, actually, no, I will go back. It is wrong. And the problem was that problem may not be the right word. As we go through, as humanity goes through its existence, one of the nice things that happens is that our ability to understand our universe improves. Our techniques for making observation improves, and our technology to make observations or do experiments also improves. And so as we progress, so does our capacity to make better and better and better measurements or better and better observations. And for the Ptolemaic model, the problem that arose was that the predictive nature of the model continued to fail, such that and if we go back to the scientific method, scientific method basically says, all right, if you have a hypothesis, you need to test it. In this case, the hypothesis is the model itself. The question may be, where is Mars a year from now? The model is going to tell you it's right there. And you test that by waiting a year and seeing if Mars is indeed right where it said it is. And it was not frequently, but it was continuously over the next 1,300 years, it was shown that the Ptolemaic model failed, where it would say that the planet should be in this location at this time, and when you actually observed it, it would be noticeably off. And again, as we got better at doing our observations, the more we noticed it was off. So you're left with two options again. Either A, you can reject the model entire, or two, you can change the model, tweak it. And that's unfortunately what people did for 1,300 years. They added epicycles onto epicycles onto epicycles to the point that the system, the final system before it was finally rejected, involved 66 epicycles. So again, for each of those epicycles, you needed to do geometry. You need to basically solve some geometry in order to figure out where something was going to be. Imagine having to do that with 66 epicycles if you wanted to know what all the stars, planets look like. So, while I have never been able to find the reason for it, I suspect that is the reason why Nicholas Copernicus, around the 1550s, a Catholic trained, I don't believe that he was actually ordained, but he was definitely of the Dominican order of the Catholic faith. And he decided that he was going to come up with his own model. And I suspect that the reason for that is because the Ptolemaic model was very unwieldy to use, and it was wrong. Observations illustrated that it was not predicting things well. And so he decided, well, let me give this a shot. Let me look at the underlying assumptions of the Ptolemaic model. Primarily, the assumption that the Earth is the center of the universe. Let's see what happens if we make the sun the center of the universe, and we make basically the planets go around the sun, and the only thing that actually revolves around the Earth is the moon. And so he came up with the heliocentric model, as has been called. It got that his model again accurately illustrates what retrograde motion looks like. It also accurately determines what Venus should look like. One of the other observations, particularly, this became more of an issue with Galileo. Galileo noticed, hey, Dr. Nimrod. Galileo noticed through a telescope, if he observed Venus, that Venus underwent phases very much like the moon. And as I'll talk about later on when it comes to the moon itself, these phases occur because of the relative geometry between the observer, the object, and the sun. So in this case, the observer, Venus, and the sun, given the geometry between those three objects, you're going to get different phases because part of the planet is going to be blocked out. It is going to be unlit, rather. You're only going to see the portion of the planet that's currently being lit by the sun. The Ptolemaic model, depending on how you work it, can give you that Venus will go through phases, but those phases will be inaccurate. For instance, as you can see here, it shows that that Venus will actually get larger in angular size as it gets thinner. As it goes from a half to a crescent, it gets larger in angular size. The Ptolemaic system actually predicts quite the opposite. That if it goes through, if you can get it so that it will show you a crescent phase, it actually gets smaller as Venus would go into that. So it really was a definitive nail in the Ptolemaic coffin because Ptolemy's model cannot replicate this. It cannot replicate the phases of Venus. Now, there are problems with the Ptolemaic, or the Copernican model. The Copernican model, while it challenged the assumption of the Earth being the center of the universe, it did not challenge, and again, I don't know why, but it did not challenge the assumption of circular motion and circular orbits and uniform circular motion. So Copernicus's model, as he described it in his omnibus of celestial bodies or movement of celestial bodies, I can't remember what the name of it is. It's Latin. Something about the motion of celestial bodies. In the book that he wrote and got published pretty much near when he died, because he was afraid of the repercussions of what the church would have to say about it, he used circular orbits, and unfortunately, he also still had to use epicycles. Not 66 of them, but he still, had to rely on using epicycles in order to get things right. As it turns out, at the time, particularly when it comes to the gentleman that I'm going to talk about next, the Copernican model was no better or more accurate at predicting planetary positions in the future than the Ptolemaic model was. They are basically the same. Given the tolerances or given the ability to measure, to observe a planet's position, Ptolemy and Copernicus, their models basically were within the error bars. One could not be favored more than the other. But, and this is probably the saving but, is that the Copernican model can do something that the Ptolemaic model never could in any of its iterations. The Copernican model says that if you know the distance from the Earth to the sun, I can tell you what the absolute distance to any of the planets are. Because the Copernican model was able to accurately and surprisingly accurately, like astonishingly accurately, determine the relative distances between planets. For instance, it said that Mars would be 1.5 times as far away from the sun as the Earth is. It said that Jupiter would be 5 times as away from the sun as Earth is, roughly speaking. And it's startling to me how accurate he was using this circular model, again, using pen and paper. So Copernicus could tell you something that Ptolemy couldn't, is that if you knew the distance from to the Earth to the sun, you could find the absolute distances of the planets in real space. Which might be why folks like Tycho Brahe, he's number one on dead astronomers I'd really like to have a beer with. And yes, I do have a list down to 5. Tycho is number one. Although I say Tycho, and honestly, now that I've got international folks, I've been told that the proper pronunciation is Tuco, but I just for some reason want to default back to Tycho. Anyway, I'm going to call him Tycho until I get proven otherwise. Tycho Brahe was a Dane, and much like many of the scientists or the observer scientists or physicists of the up until, say, the modern era, he was an independently wealthy individual. Tycho is, as if you've watched one of my my YouTube shorts, I refer to him as the Tyrion Lannister, only taller. The man got his nose chopped off in a duel. The duel was with one of his one of his distant cousins about the validity of a certain mathematical proof. So the dude lost his nose, literally fighting with a sword about math. He liked to get drunk a lot. He had a pet moose that he also liked to get drunk, unfortunately for the moose, because while a drunken moose can climb upstairs real good, a drunken moose doesn't come downstairs real good. So sadly, the moose perished. Sad. Tycho would throw extravagant parties. He was very, very full of himself, to the point that I believe this is in the second of his observatories. He actually built 2 different observatories. The second one of which has this mural in the observatory of him greater, larger than life, making observations, so that all of his assistants can basically know, who's paying your, who's funding you, who's giving you your paycheck, who's writing your paychecks. It's me, the dude on the wall. Yeah, that guy. Ultimately, and Tycho actually had an ignominious death. Now, the exact nature is up for some debate, but it's pretty agreed on that what happened was that Tycho was hosting, I believe it was some kind of duke of Danish duke, some kind of high nobility of Denmark. And really what he was doing was probably hosting him so that he could, get money out of him. Well, the Danish culture at the time basically dictated that if you are of lower rank when at the dinner table, you do not get to leave. Basically, the first person to leave is the person of highest rank, and then it went down from there. So when the Duke was at the table, no one can leave until the Duke left or got up. And apparently Tycho had a little too much to drink, and these were like 7-course, probably all-night affairs. So huge, huge event. Probably drinking like crazy. And of course, as you do, dude had to pee at some point. Probably pretty early on. He died basically a few days. He was bedridden the next day and died a few days later. Whether he died of a burst bladder or a bladder infection is up for some debate, but it was definitely because the man could not take a piss in a appropriate amount of time. So yeah, I loves me some Tycho Brahe. He is definitely numero uno on dead astronomers I would love to have a drink with. Well, let's get back to the science. Why am I mentioning this dude at all? I'm mentioning this dude because he is on record as being the best naked eye observer pretty much ever. Now, some modern folks might be able to take that claim, but definitely during the Renaissance or late 1500s, early 1600s, somewhere in there, Tycho made the best observations of anyone, anywhere, who wrote it down. Tycho's observations were so good that his error bars, or his precision, was down to 8 arc minutes. What that means, his precision was down to a single arc minute. He could accurately tell you the position of a star in the night sky to 1/30th of the width of a full moon. So take the full moon. So go outside next time. I think it's full moon right now. Go outside, look at the full moon, slice it in your mind in 30 equal parts, And Tycho was able to tell you where the position of something in the sky was to an accuracy of a 30th or one of those slices. He did so using the instrument that you can see here. It's called a meridional instrument. It's an arc. It's a huge, basically, arc, I guess, instrument. And what you do as an astronomer is, as an observer, is you basically sit next to it, and you are only worried about objects that are on the meridian, that line that runs through due north, through zenith, down to south. And what Tycho would do is, as a star would transit, would get onto that line, he would basically tell somebody, hey, what time is it right now? Write that time down, and then he'd use an instrument to figure out what the altitude of that object was, of that star was, at that particular time. And using that technique, that's how he was able to determine the positions of things so very accurately, specifically Mars. Now, the reason why Tycho was doing this because it was very in vogue at the time to try to come up with your own cosmology. It was very in vogue to try to come up with your own model of what the universe looked like. And Tycho, being Tycho, was like, well, you know what? I need to have my cosmology, which he did. It doesn't work, but there is a Tycho Brahe cosmology out there, a model of the solar system, if you're interested. What he did was he was like, let's split the difference. What I'm going to say, the Earth is the center of the universe, the sun revolves around the Earth, and then everything else revolves around the sun. So he wanted his cake and eat it too. Now, while Tycho was a very, very good observationalist, and apparently he was something of a mathematician, although not so much of a dualist, he either didn't have the capacity to, or more than likely didn't have the inclination to create his own mathematical model. And so he hired somebody to do it. In present day, in the modern era, ultimately what this was that he hired a postdoc. He hired a postgraduate researcher to basically do the math for him. This is actually fairly common these days. And that postdoc was a gentleman by the name of Nicholas Copernicus and Johann Kepler, a German individual who was a mathematician by trade. And what he was charged to do was that Tycho basically said, here, have all of my observations, make math, do the math thing, make me a model. And so that's what Kepler did. And actually, the story gets even more crazy because when Tycho died, Kepler wasn't done yet, and he actually had to steal the data from Kepler, or from Tycho's family, because when things went into probate, Tycho's possessions were being highly contested over, including his observations of the sky, and Kepler literally stole them and left so that he could complete his work. Awesome stuff. Couldn't make this up. Anyway, took him a while, but he finally was able to do it. And the hurdle that he had was because of Tycho's precision. As I said, Tycho's precision was 1 arc minute. Kepler was confident in Tycho's ability to distinguish an object's position within 1 arc minute. Therefore, when he applied models like the Ptolemaic model or the Copernican model, Tycho, okay. All right, Tycho. When he applied those models, he got a discrepancy of about 8 arc minutes, which is tiny. It's very small. You probably wouldn't really notice it with your naked eye, just casually. But with an instrument, particularly Tycho's instrument, you would notice it. He did, and so Kepler was convinced, rightly so, that this was a real effect. And so he continually beat his head up against this wall until he finally just dropped all assumptions, or all the Aristotelian assumptions. Basically said, all right, let's put the Earth at the center of things, and now let us get rid of things like circles, get rid of things like uniform motion. And he developed his 3 laws of planetary motion. Kepler's first law states that planets orbit in ellipses, or orbit in an elliptical orbit. Now, that includes circles. What is an ellipse? An ellipse, and I'm not a mathematician, so there's probably a much more elegant way of stating this. But an ellipse is a curve around a central point that is described by 2 foci, or 2 individual focuses. So think of a circle but squashed. Then the amount that it's squashed, technical term, is known as the eccentricity. And it ranges from 0 to 1, or very, very nearly 1. An eccentricity of 0 means the 2 foci lie on top of each other at the center of the center of the figure. That gives you a circle. The distance from the curve to that center point is equal as you go all the way around. That's an eccentricity of 0. As the eccentricity increases, the figure gets more and more squashed. So an eccentricity of 0.1 is more oblong than an eccentricity of 0. An eccentricity of 0.5 is even more so. An eccentricity of 0.9 is even more so. So, for example, this actually, ignore this. The Earth's orbit is not so elliptical. It's actually it's not. If you were to visualize it at this scale, you really wouldn't see that it's an ellipse. But comets have very elliptical orbits. And if you were to visualize them, plot out the data, and look at their orbits, you could definitively say, oh yeah, that's an ellipse. So Kepler generalized orbits. He basically said that instead of requiring an object go around the sun as a circle, he said, well, it can go around as an ellipse. Yes, it's possible for it to be a circle, but more than likely, it's going to be elliptical. And the key, as I've said, the way to describe an orbit is through its eccentricity, how squashed it is, and then also through its semi-major axis, or effectively how big it is. So you can kind of think of that as analogous to radius. You can see on this figure, the semi-major axis is the distance from the center of the figure through one focus to the curve. If you want a more mathematical description of an ellipse, it's right there for you. E is eccentricity, theta is the angle around the curve, and then r is the distance to the curve. So that's Kepler's first law. Kepler's second, so the first law basically got rid of the circular orbit business. The second law got rid of the uniform circular motion business. Let me just do that. There are a couple of different ways to state Kepler's second law. My favorite is equal areas and equal times. What this states is that a planet will orbit around the sun. When a planet orbits around the sun, it will sweep out equal areas in space in equal times. So, for example, in the upper left, we have a really sophisticated drawing of the Earth, this black figure. Earth is the black figure, sun is the orange figure. And then 3 months later, it's over here. And you can basically calculate what the area that has been swept out is. You then wait another 3 months, and then you have another area, which you can then calculate what that is. And what you'll find is that those two areas, area 1 and area 2, are equal. Same thing if you do it this way, 6 months. If you go wait 6 months and then wait another 6 months, you get, obviously. Does that make sense? That's got to be 3 months and 3. I don't know. Anyway, the idea is, I don't think this figure is entirely accurate, but the point is equal areas and equal times. It's going to sweep out these equal areas based on an equal increment at which you take the planet's position. Now, what we find is, because it's an ellipse, because these orbits are an ellipse, these areas, while they are no, that statement was going to be completely wrong. A consequence, let's go back the other way. A consequence of this, of equal areas and equal times, is that the planet does not move uniformly. The planet does not move uniformly throughout its entire orbit. Actually, it is constantly changing its speed. It's actually also constantly changing its velocity, but the rate at which it goes around the sun is not constant. It's constantly changing, and it does so. And in addition to that, what it means is that when a planet is closest to the sun, or in a position known as perihelion, at or near perihelion, the planet is going to move faster than when the planet is at aphelion, or furthest away. So if you looked at this sort of exaggerated image, when it came by the sun at perihelion, it zipped by and then slowly get to aphelion, come back around, zip by, and do one of these numbers all the way around. The physical reason for this is something known as the conservation of angular momentum. Best seen with ye old figure skater. What the conservation of angular momentum is think of it as the amount of rotational energy something has. And that is dependent on three things. That is dependent on the distribution of mass of the object. It is just dependent on the velocity at which the object is spinning. And it depends on the mass itself, of the mass of the object, how that mass is distributed, and the velocity at which it's spinning. So imagine that figure skater. You have a figure skater with their arms out. They have a certain mass. They're going into their spin with a certain velocity, and they have their arms out. So their mass is fairly outwardly distributed. And then they pull their arms in. So they make the mass distribution smaller. Because obviously they're not going to go on some kind of weird fasting diet. Their mass is the same, out and in. So if the distribution of mass gets smaller, then the velocity has to go up. The spin rate has to increase in order for momentum to be conserved, because energy is conserved. So here you can see that as so if you look at the entire system, and the entire system is the planet and the sun, as the planet gets closer to the sun, the mass distribution gets smaller, or gets closer together, and therefore the spin gets faster. And then as the planet goes out, the mass distribution gets larger, and it spins out, or it spins slowly as it goes out. Oops. And then, so perihelion, aphelion, perihelion closest to the sun, aphelion, Greek for furthest away from the sun, analogous to perigee, which is closest to the Earth, and apogee, which is furthest away from the Earth in an orbit. And then lastly, I will talk about Kepler's third law. or his harmonic law. Now, if you were to Google this, you would more than likely come across the famous p squared equals a cubed, or the period of the planet squared is equal to the semi-major axis cubed. That's kind of right, but that depends on the units you use. So here you can see that semi-major axis is given as the variable r. Period is given with the variable p. So if the period is in years and the r is in AU, or the average distance between the Earth and the Sun, then that's right for planets in the solar system. If you were to graph that up, if you took the period of Mercury, squared it, and plotted that versus its semi-major axis in AU cubed, and then did the same for Venus, then Earth, then Mars, you would see that it was a straight line. That's not how Kepler figured it out, or that's not how Kepler stated it. Because again, Kepler didn't know what the distance, what the AU was. He didn't have a number for the AU. He didn't know what the distance between the Earth and the Sun was. He had guesses, he had some estimations, but he didn't have anything he really wanted to hang his hat on. That would only occur later in the 1800s during a Venus transit of the Sun. What Kepler actually stated was that if you took the period of a planet relative to another planet, in this case Earth, and you squared that quantity, and that would be equal to the semi-major axis of the planet compared to another planet, Earth, cubed. What this did was that it conveniently or inconveniently, depending on how you want to look at it, disguised some physics, which I'll get into later today in my next lecture, talking about Newton's laws and how it relates to orbits, is that there are certain factors, very important factors, spoiler alert, mass, that go away if you look at this as a ratio. If you look at this as a ratio of period of one planet with respect to the other, a semi-major axis with respect to the other, another, things like the gravitational constant, pi, mass, they get canceled out. They go away. They do not factor. So it's a very, very simple idea, very simple, what's the word I'm looking for? Description, I guess. It's a very simple way of figuring out what the distance and the period of these planets are with respect to each other. The problem is that it is only applicable to planets going around the sun, as Kepler wrote it. It's only applicable to planets going around the sun. It does not hold or moons going around a planet. So you could use the same formulation of period over period squared equals A over A cubed. You can use that same formulation if you're talking about trying to figure out the relationships between, say, Io to Ganymede. So long as you're talking about one thing orbiting around a specific object, then you can use that formulation. But the problem is that you cannot generalize it to anything else. It is very specific. It is very specific to the situation you're dealing with. It wasn't until Newton came along onto the scene that Kepler's harmonic law became much more powerful. And like I said, we'll get into that next time in my next lecture, hopefully, which will be in about 3 hours from now, if assuming that my other work doesn't get in the way. So as always, I hope you enjoy this lecture. I hope you continue to watch along with these things. Thank you for everyone who is in the chat. If you have any questions, I've been trying to keep my eye onto it. you? I was trying to keep an eye on it, but as always, if you have questions, feel free to put them in the chat. I have been looking at the comments to make sure that if there are any questions in the comments, I can answer those quickly. I'm losing my words as I get older. And yeah, if you enjoy this content, please like, share, and subscribe. If you would like to help us out here at George Mason financially in terms of our research, or excuse me, our outreach efforts, please consider becoming a patron of mine. You can find the link in my about page. All proceeds go to buying equipment and paying our tour guides to go out to Cub Scout places, Girl Scout places, elementary schools, and so to spread the word of astronomy and allow us to use our telescopes and inflatable planetarium to good use. So, all right, with that, can you start from the beginning? Sorry, Claude, you're going to have to put it on replay. But I have had a student ask me that in real time. A student came up to me after class and said, "Sorry, Professor, I missed the first 45 minutes of your lecture. Can you please give me a recap of it?" I can't remember what I said, but it was something akin to no. So there you go, Glenn. No. All right, all. I think there was something else I was going to say, but I've completely forgot what it was. All right. Peace out. Clear skies. I'll talk to you guys later.